Hello chemistry students, here with another video to fill in on my promise and teach you how the solubility pyramid works in order to determine what the states of matter are of various chemicals that you might come across. So the solubility pyramid sorts different ions or different things you might find in ionic compounds into groups or tiers that allows you to determine what's the likelihood of them being soluble or being able to be dissolved in aqueous solution in standard conditions, so at room temperature, etc. So the way this works is that we have this separated into three tiers. We have one tier at the top where any compounds that contain these ions, either nitrate, ammonium, or an element from group 1 of the periodic table, such as hydrogen, lithium, sodium, potassium, etc., belong in tier 1. And typically if you see these chemicals, they can always be dissolved. They can be found in soluble solutions, in aqueous solutions at room temperature. So if you see something from here, it will typically be able to be found in an aqueous solution. Tier 2 is mostly soluble, so when you see a compound that has a sulfate group in it, or a chloride, or a bromide, or a fluoride, anything from group 7A of the periodic table, those you can mostly expect to be soluble or be able to be found in an aqueous solution unless they're paired with one of these positive ions from group 3. So if you see, for example, calcium sulfate, you would expect that to be soluble. Whereas if you saw silver paired with sulfate, you would expect that to form a solid and not be able to be dissolved in solution at room temperature. The final tier is tier 3, and tier 3 compounds are almost always form insoluble solids, unless, of course, they're paired with tier 1. So being in tier 1 overrides being in tier 3. So if you see a compound that contains a carbonate group, almost always you'll expect that to form a solid in standard conditions. It would not be able to dissolve in aqueous solution. If you see a phosphate group, same thing. If you see a hydroxide group, same thing. However, if you see a hydroxide paired with, say, sodium hydroxide, since sodium is in group 1, it overrides being in group 3. So you would expect sodium hydroxide to be soluble or to be in the aqueous state. In the same way you would expect ammonium hydroxide to be in the aqueous state. So let's just do some practical examples to see how we can do this. So, first example is copper 2 sulfate. So the chemical formula for this would be CuSO4. Cu has a 2 plus charge, SO4 has a 2 minus charge, so there's balance. If we look at our solubility pyramid, we see that this contains a sulfate. Sulfate's in the second tier. So unless it's paired with one of these exceptions, we'd expect that to be aqueous, so, to be soluble in solution, or to be aqueous. So we see that sulfate is not paired with silver, barium, mercury, or lead. So if we saw this in a chemical equation, we could predict that this would be aqueous. And in fact, it is. I have a bottle of copper sulfate right here. And we can see that there's no solid chunks in this bottle. It's all aqueous. It's an aqueous solution. Silver iodide, if we take a look at silver iodide, the chemical formula for that would be AgI. Ag takes a +1 charge. I takes a 1 minus charge. So this is a balanced formula. If we look at this, we'd see where in our solubility pyramid does this fall. Well, I is a group 7A element along with chlorine, bromine, and fluorine. It's one of the halogens. So we say, okay, it should be soluble unless it's paired with one of these exceptions. And we say, aha, it's paired with silver. So because it's paired with silver, it goes from being soluble, from being expected to be aqueous, to being expected to be solid because it's paired with something from group 3. So this we would predict to be solid. Now, I don't have silver iodide in a bottle here because obviously it wouldn't be soluble, but I can make some. So if we do a double replacement reaction using this silver nitrate, something from group 3, paired with something from group 1, so group 1 overrides, this is a soluble solution, with sodium iodide, we would expect that to be insoluble. We would expect it to be insoluble and to form an insoluble solid. However, I did not bring my silver iodide. So I did not bring my sodium iodide. So let's turn this into silver hydroxide. So AgOH, we definitely would expect to reside in the bottom tier because both of these are in tier 3. We would expect this to be solid. Again, I don't have silver hydroxide, but I do have the silver nitrate, and I do have ammonium hydroxide. So if I take some of each of these and combine these two clear solids, what we would expect to get is an insoluble precipitate. So we add a couple of drops of our silver nitrate. We see that it's clear. If we then add a couple of drops of ammonium hydroxide, we'll complete a double replacement reaction that I'll draw for you in just a minute. And what we get is a gunky insoluble precipitate. The mixture immediately becomes cloudy. And what we're seeing there is the silver hydroxide is no longer able to be soluble. It's no longer able to be aqueous, and it settles out of solution in this kind of gunky brown mess. So the way we would predict that would happen is, again, we were mixing silver nitrate, AgNO3, which is aqueous. We know that it's aqueous because we can see it in a bottle, with ammonium hydroxide, NH4OH, also aqueous, we can see it in a bottle. And what we would get would be silver hydroxide plus ammonium nitrate, NH4NO3. This we would expect to be aqueous because both things appear in the top tier, and this we would expect to be solid. And since we know that this is solid, we would predict, before we even mix these chemicals, that it will form this insoluble precipitate that we see here. So we can use our knowledge to predict that silver hydroxide will be solid before we even do our experiment, which is the power of this solubility pyramid. Again, quickly, I wanted to do some more experimentation for you, but this is taking a little more time than I thought. Ammonium hydroxide, NH4OH. NH4 belongs in the top group, OH is in the bottom, NH4 overrides OH, and we would expect this solution to be aqueous, which indeed it is because it's in this bottle. Soluble. Lead sulfate, PbSO4, contains a sulfate group, so it's from this tier. We would normally expect it to be soluble unless it's paired with one of these elements. It's paired with lead in this case, which is one of the exceptions. So we would expect lead sulfate to form a solid, to not be able to be soluble in solution. I hope this helps with use of the solubility pyramid. Let me know if you have any more questions. Sorry that I didn't actually bring the sodium iodide. I expected to do that experiment instead. But hopefully the replacement quick substitute that I was able to do because I understand the solubility pyramid was able to stand in and show you what I meant by that. Hope that helps. Let me know if it doesn't. I will see you in class.